American crews examined captured King Tiger, realized 88mm couldn't pen jumbo frontal armor. A burnt-out German Panzerkampfwagen Tiger Ausf. B stood under American guard at the Isigny Ordnance Depot. Its weight, 68 tons. Its frontal armor, 180mm, sloped at 50 degrees. Its main gun, the 8.8cm KWK-43L/71, was reputed to pierce any Allied tank before they could return fire. But when United States engineers from the Aberdeen Proving Ground fired the same 88mm gun at the frontal plate of a recently delivered M-Four-A-Three-E-Two Jumbo Sherman, the shells bounced. Not once, but repeatedly. The weapon feared across Europe had failed against an American tank barely known outside its own divisions. That result, recorded in an official ordnance report in February 1945, challenged the entire myth of German armored invincibility. The numbers were about to tell a story that propaganda could never silence. 11 July 1944. The hedgerows of Normandy. British liaison officer Captain Harold Dinsdale laid a typed contact report onto a divisional intelligence table. The paper bore a simple, chilling notation. New heavy tank encountered. Glassy appears immune to 6-pounder and 75mm. The German Schwer Panzerabteilung 503 had deployed the first Tiger II in combat that morning. Allied units along the Caen perimeter reported complete gun immunity below 500 yards. British 75mm and 6-pounder rounds ricocheted from its glassy like pebbles off a fortress wall. United States Intelligence Telegram number 1929, filed 15 July 1944, noted with rare alarm, armor believed impenetrable to all weapons now fielded. The expectation was catastrophic. Allied commanders anticipated local breakthroughs forced by armor immunity and long-range fire. Staff officers calculated that a single Tiger II could anchor an entire defensive sector or spearhead a counterattack that conventional tanks could not stop. The reality arrived more slowly, buried in operational diaries and unit returns. That same week, Schwer Panzerabteilung 503 recorded multiple non-combat losses. Overheating, final drive failures, and fuel shortages. German unit returns listed vehicles immobilized before contact. Of the 45 tanks committed, nearly half were lost to mechanical breakdown within the first 72 hours. German design authority Erwin-Itters had argued for thick frontal plates and the long 8.8cm gun. British staff officer notes from mid-July described unprecedented sloped thickness. The numbers were staggering by any measure. Tiger II Glassy, 150 to 180mm nominal, angled 50 to 55 degrees. Gun, 8.8cm KWK-43L/71. Firing armor-piercing capped ballistic cap rounds designated PZGR-39/43 and armor-piercing composite rigid rounds designated PZGR-40/43. Curb weight, approximately 68 to 69 metric tons. Maybach HL 230P30 engine, 700 horsepower. Road range, according to the technical pamphlet, 120 to 170 kilometers. Field reports often recorded far less. The promise of invulnerability invited tactical overconfidence. Mechanical attrition erased much of the supposed combat power before contact. A British AFV technical report from mid-July 1944 stated flatly, front hull presents immunity to current service shot at normal battle ranges. By September 1944, heavy battalions reported operational readiness below 50%. The tank's greatest enemy, it seemed, was not always Allied guns. Of the 489 Tiger IIs produced by war's end, fewer than 120 remained operational by late autumn 1944. The mathematics of war were already rendering judgment. A courier arrived at Versailles headquarters with crates labeled recovered armor sections, sample cuts for hardness and microstructure inside. Precisely measured sections of German tank plate, each tagged with recovery coordinates, estimated thickness, and preliminary field observations. Field rumors credited the Tiger II with absolute superiority. Ordnance analysts insisted only controlled measurements could determine true resistance and gun performance. The decision was made to centralize captured material exploitation under a single coordinated effort. The Ordnance Technical Intelligence Section, ETO-USA, was tasked to capture, measure, and fire test enemy material. Coordination with Aberdeen Proving Ground in Maryland ensured metallurgy and ballistics work met United States standards. The depot at Isigny, Normandy, was designated to receive heavy German wrecks for systematic disassembly. Lieutenant Colonel John K. Barton led the technical teams. His mandate was clear: replace speculation with data. Every plate thickness, every weld quality, every engine hour logged. All of it was to be measured, recorded, and analyzed. Preliminary weighbridge readings logged approximately 68,000 kilograms. Bridge classification and transporter limits made cross-river moves extraordinarily difficult. Standard treadway bridges were unsuitable without reinforcement. An ETO-USA memo circulated in late October warned, transport of Tiger B on Standard Bailey Bridge is contraindicated. Reroute via heavy ferry or reinforce. Measured transmission life on some returns. Approximately 700 kilometers. By comparison, a Sherman M-Four-A-Three could expect over 3,000 kilometers under normal conditions. The Tiger II's engineering excellence came with a hidden cost. Every component operated at the edge of material limits. The decision to establish a European test lane meant evidence would replace anecdote. Within months, firing data would challenge long-standing assumptions about German armor superiority. An internal note calculated that the fuel and bridging footprint for one Tiger II equaled that of a United States Sherman platoon, a strategic imbalance hiding inside a single vehicle. The machinery of analysis was now in motion. Across the Atlantic, Aberdeen Proving Ground prepared test protocols. In Normandy, engineers sharpened cutting torches and calibrated measuring instruments. The legend was about to meet the laboratory. A maintenance NCO chalked Jumbo on a newly issued cast-nose Sherman with heavy mantlet cheek armor. The vehicle looked different, bulkier, heavier in the turret, with a frontal profile that suggested something other than the standard Sherman silhouette. The M-Four-A-Three-E-Two was intended for assault and breaching, not tank duels. Designed to lead columns through fortified towns, it carried additional armor welded and cast onto critical frontal surfaces. Frontline reports, however, noted exceptional survivability against German long-barrel guns at short range. Hull front, cast nose. Approximately 152 millimeters at approximately 47 degrees. Mantlet with weld-on reinforcement. Up to 178 millimeters total thickness. Turret walls. Heavy cast sections, thicker than any previous Sherman variant. Standard armament. 75mm M3 gun initially, with some units later upgunned to 76mm M101. Production: 254 units. Unit cost: approximately $54,000 per vehicle, nearly double a standard Sherman. Weight: approximately 42 tons, pushing the limits of the Sherman suspension. Effective resistance studies projected approximately 190 to 210 millimeters rolled homogeneous armor equivalent on the cast curve at certain angles. The geometry of the cast nose, combined with high-quality American steel, created unexpected defensive capability. A December field report attributed 14 non-perforating hits from a Panther to one Jumbo leading a column near the Ardennes, with the tank remaining operable. Sergeant James P. Heron's crew counted the strikes after the engagement. Gouges, spall marks, and craters, but no penetrations. The crew walked away unharmed. A United States divisional message from December 1944 recorded, "Assault Jumbos proving immune frontally at street ranges. Recommend retention at lead of columns." Unanticipated survivability flagged the Jumbo as the logical United States reference plate for evaluating high-energy enemy shots. These data reached ordnance laboratories before an intact Tiger II arrived for fire comparison. The stage was set for a test that would redefine understanding of armor and firepower. The vehicles were in place. The questions were forming. Soon the guns would answer. Chapter 3, 385 words. Engineers of the 291st Engineer Combat Battalion circled a fuel-starved heavy tank abandoned during the retreat from the Amblev Valley. The vehicle sat silent, immense, its long gun barrel angled toward the western road it would never travel again. German doctrine envisioned heavy armor preserving combat power by shock and long-range overmatch. Kampfgruppe paper left multiple vehicles for lack of fuel and route capacity. This Tiger II, vehicle number 213 of Schwer SS Panzerabteilung 501, was one of them. The field inventory sheet, filed 29 December 1944, read, "Gun serviceable. Vehicle immobile due to fuel unavailability. Exterior indicates no penetrating impacts. Breech inscriptions confirmed manufacture. Krupp AG Essen, 1944. The traverse drive was electric hydraulic, manufactured by Siemens. Every component bore the marks of Germany's finest industrial effort, and its growing inability to sustain that effort in the field. 2 M26 armored recovery assets, additional tractors, and a 3-day effort moved the hull roughly 10 miles. Photogrammetry and measuring tapes recorded plate dimensions. Temporary splints braced the nose for transport. The main armament remained operational. The armor showed no known perforations. An intact gun and frontal plate enabled a controlled test the European theater had not previously achieved. But the manpower required told its own story. The effort to tow the single wreck exceeded the crew count of an entire 5-tank Sherman platoon, a measurable cost before a single shot was fired. Captain Robert M. Bellinger, overseeing the recovery, noted in his log, "The vehicle represents pinnacle of German armor engineering. Also represents logistical absurdity. Every component is over-designed. Recovery effort, excessive." The tank arrived at Isigny on the 3rd of January, 1945. Ordnance teams photographed it from every angle. Engineers prepared cut lines. Metallurgists sharpened micro-hardness testers. The legend was about to be dissected, measured, and understood, not as myth but as metal, chemistry, and mathematics. The test that would rewrite armor history was days away. Torch crews marked cut lines in chalk across the Tiger II's glacis. The cuts would yield slugs. Sample sections lifted to a bench for micro-hardness measurements, macro-etch analysis, and metallographic examination. The Tiger II's reputation assumed a homogeneous, consistently hard plate across all surfaces. Sample cuts revealed variability associated with late war supply stress. Brinell hardness readings on frontal sections measured approximately 260 to 290 HB. Side plates measured around 250 to 265 HB in tested samples. By comparison, the United States armor plate for the M-Four-A-Three-E-Two Jumbo consistently achieved 240 to 260 HB with tighter tolerances. American steel mills maintained quality control even as production scaled. Turret face, approximately 180 mm rolled plate. Turret sides, approximately 80 mm, a known vulnerability. Hull roof, only 40 mm, a dangerous weakness to artillery airbursts and top-attack munitions. Weld quality varied across the hull. Some inclusions and lamination indications appeared in macro-etch examination. Engineers noted that late-war German steel showed signs of alloying compromises. Reduced molybdenum, substituted manganese, and inconsistent heat treatment. An OTIS note, filed as T-Series Memo T1247, concluded, "Excess mass with diminishing ballistic return on frontal array. Side armor insufficient to justify total weight." The metallurgists calculated a sobering ratio. The Tiger II's frontal improvement over a Panther was approximately 15% by resistance. Mass, however, grew approximately 40%. An unfavorable exchange for strategic mobility, fuel consumption, and production capacity. The engineers also examined the suspension, transmission, and final drives, where patterns suggested chronic overload. Bearing surfaces showed galling. The Maybach HL 230P30 engine, while powerful, operated at maximum stress under the vehicle's weight. Oil analysis revealed metal particulates consistent with accelerated wear. One senior metallurgist, Lieutenant Harold Fisher, summarized the findings in his report. The Tiger II represents an engineering philosophy that prioritizes single engagement dominance over sustained operational capability. It is a dueling pistol in an era that requires repeating rifles. Metallurgy suggested high frontal immunity but increased susceptibility to mobility kill and artillery effects. The data confirmed the logic of testing enemy shots against United States cast armor. The next phase would answer the critical question: could the feared 88mm gun defeat American heavy armor? A bench technician logged muzzle velocities against a chronograph screen. Propellant lots were labeled by production plant: Wolf and Company, Walsrode, Dynamit AG, Troisdorf, and others. Each lot would be test-fired to measure actual performance against manual specifications. Manual tables claimed exceptional penetration. Lot-by-lot velocity checks showed the war's chemistry and manufacturing strain eating into those promises. The 8.8cm KWK 43L/71 was Germany's most powerful tank gun. Ammunition types included PZGR 39/43, an armor-piercing capped ballistic cap round, PZGR 40/43, an armor-piercing composite rigid round, and SPRGR 43, high explosive. Recorded muzzle velocities for APCBC rounds measured near 1,000 meters per second. APCR rounds measured around 1,130 meters per second in sample shots. These figures approached but did not always meet the manual specifications. United States Standard 240 Burnell hardness plate conversions indicated approximately 202 mm penetration at 0 degrees obliquity at 100 meters range. At 1,000 meters range and 30 degrees obliquity, penetration fell to approximately 165 mm under ideal lot performance. German manual D656/27 predicted higher figures, but propellant quality tests revealed a troubling pattern. Several propellant lots measured velocity shortfalls on the order of tens of meters per second. Engineers attributed the loss to nitration and grain stability issues, evidence of Germany's collapsing chemical industry under Allied bombing. A bench log entry read, "Observed muzzle velocity variance exceeds table allowance. Suspect late war filler inconsistency." If the gun's energy was compromised by propellant variance, its theoretical penetration margin against high-quality United States cast plates narrowed further. The weapon famous for killing Soviet IS-2 heavy tanks at 2 kilometers range now risked underperforming its own specification sheets. Engineers also measured barrel wear. The rifling showed erosion patterns consistent with high-pressure loads and aggressive propellant chemistry. Barrel life estimates suggested fewer than 500 effective full-charge rounds, a limitation in extended campaigns. The mathematics were unforgiving. Velocity loss translated directly to penetration loss. A 10% reduction in muzzle velocity could reduce penetration by 15 to 20% at range, depending on obliquity. The gun's reputation rested on performance it could no longer consistently deliver. The firing test against the Jumbo would settle the question: theory versus reality, specification versus field performance, legend versus laboratory. Range flag up. A static mount secured the 8.8cm KWK 43L/71, pointed at a cast jumbo nose set to replicate service attitude and angle. Observers took positions behind protective berms. Chronographs were calibrated. Camera crews prepared high-speed film. Expectation: the 88mm gun would defeat any Allied plate head-on. Conventional wisdom held that German high-velocity guns dominated Allied armor at all practical ranges. The test would confirm or challenge that assumption. Test configuration was precise. Range: 500 yards. Target: M-Four-A-Three-E-Two cast nose. Approximately 152 mm thick. Angled at 47 degrees from vertical. Representative curvature preserved to match field geometry. Rounds: series of APCBC strikes. Hit logs recorded angle, strike point, and plate response. Observers watched for cracking, spall, and backface signature. The first shot rang across the range. Impact: the shell struck the cast nose and deflected upward, leaving a deep gouge but no penetration. Engineers marked the strike. Camera crews reviewed the footage frame by frame. Second shot. Another impact. The projectile cracked on contact, fragments scattering. The plate held. Observers noted partial surface cracking without spall, no penetration. Shot after shot, the pattern repeated. The 88mm gun, firing at 500 yards, well within its effective range, could not defeat the Jumbo's frontal casting. Results, per Ordnance Ballistic Report No. 47A, filed 25 January 1945. 18 rounds fired into defined zones. 0 full penetrations. 6 partial cracks without spall. 12 ricochets off the curvature. Engineers derived a slope multiplier of approximately 1.4, yielding approximately 210 mm rolled homogeneous armor equivalent for the tested casting and angle. The cast nose, combined with high-quality American steel and favorable geometry, had created a barrier the German gun could not breach. A range note, signed by Captain Theodore S. Wilson, read, 8.8 cm APCBC failed to defeat M-Four-A-Three-E-Two cast nose. Crew space integrity maintained in all cases. The findings forced a reweighting of American priorities. Preserve cast quality and slope. Accelerate heavy 90mm HVAP supply. Reconsider tactical reliance on thick plate versus slope. The lessons were immediate and actionable. For the first time, a United States tank's frontal armor resisted Germany's strongest widely fielded tank gun in a controlled trial. The implications rippled through ordnance planning, procurement strategy, and tank design philosophy. The myth of German gun superiority, built on years of battlefield reports, had met the laboratory and failed. The war's arithmetic was changing, not through propaganda but through precision, measurement, and engineering discipline. A War Department logistics officer spread charts across a conference table. German tank output versus United States monthly completions. Petroleum, oil, and lubricants deliveries versus consumption. Spare parts production versus field demand. The numbers told a story that no single tank design could overcome. German planners banked on qualitative overmatch from heavy armor. United States planners delivered overwhelming quantity, fuel, and spares that multiplied combat power regardless of single vehicle specifications. German tank output collapsed under Allied bombing and raw material shortages. April 1944, 379 tanks per month. March 1945, approximately 55 tanks per month. The decline was catastrophic, irreversible, and accelerating. United States M4 series output, approximately 1,200 tanks per month, plus spares packages equating to approximately 400 hulls worth of components. Chrysler Arsenal, Fisher Body, Press Steel, all operating at capacity, delivering not only complete vehicles but entire supply chains of repair parts, engines, transmissions, and weapons. Fuel consumption defined operational capability more than armor thickness. Tiger II, approximately 500 liters per 100 kilometers. Sherman M4-A-Three, approximately 170 liters per 100 kilometers. Allied petroleum, oil, and lubricants deliveries into the European theater in early 1945 exceeded German national weekly production on several days. Heavy battalion readiness commonly measured around 40% in field returns during winter 1944 to 1945. Schwer Panzerabteilung 503, 507, 510, all reported chronic shortages of fuel, spare parts, and qualified crew replacements. Operational strength rarely exceeded half the roster. A German quartermaster note from late 1944 recorded, fuel allotments insufficient for training and staging, tactical marches curtailed. By contrast, United States armored divisions moved with logistical certainty. Fuel trucks followed combat units. Repair echelons operated within hours of the front. Replacement tanks arrived by rail and road, often faster than units could absorb them. Even if the Tiger II dominated a local engagement, the broader war was decided by movement, replacements, and maintenance domains where Allied systems scaled and Axis systems contracted. One Tiger II immobilized by fuel shortage represented the combat potential of 10 Shermans that never reached the battlefield. One Tiger II abandoned for lack of spare parts equaled 5 Shermans lost to combat but replaced within a week. In the quarter Isigny's data circulated through ordnance channels, United States depots issued more 90mm HVAP rounds than Germany could ship new heavy tanks, a numerical answer to a qualitative problem. The strategic equation was brutal in its simplicity. Germany fielded engineering masterpieces that could not move, could not be repaired, and could not be replaced. America fielded adequate designs that moved continuously, repaired rapidly, and replaced faster than losses accumulated. The Tiger II represented the terminal point of a design philosophy that ignored logistics. The Sherman represented the beginning of a philosophy that embraced them. History was rendering judgment, one immobilized tank at a time. An analyst drew two lines on graph paper: predicted penetration versus observed results. The lines diverged beyond acceptable tolerance. The gap represented the difference between theory and reality, between manual specification and field performance. The KWK-43's tabular performance had justified German tactical doctrine for years. Commanders planned engagements assuming the gun could defeat any Allied armor at practical ranges. The measured United States results, integrating slope and casting quality, showed the gap between assumption and evidence. Aggregated dispersion from Isigny shots measured approximately 1.9 meters at 1,000 meters equivalent. For a curved casting like the Jumbo's nose, dispersion translated to reduced hit probability and increased likelihood of ricochets. Even a centered hit could deflect if it struck the curve at an unfavorable angle. Calculated shortfall from theoretical penetration. Approximately 22% when propellant variance and slope were included. The gun's reputation rested on ideal conditions: perfect ammunition, 0-degree impact, homogeneous plate. Real combat offered none of these. Backface signature measurements indicated survivable shock for crews in the tested hits. No spall penetrated the crew compartment. Plate deformation remained within acceptable limits. The Jumbo's cast nose, when struck by the 88mm gun, performed as designed. It stopped the round and protected the crew. An Aberdeen Proving Ground memo, classified and circulated to senior ordnance staff, concluded, at existing quality levels of enemy propellant and shot, M-Four-A-Three-E-Two cast armor maintains immunity frontally to 8.8 cm APCBC at test range and angle. Confidence in United States armor metallurgy and slope geometry increased across procurement planning. The focus shifted to ammunition modernization, HVAP development and deployment, and accelerated fielding of the T-26 series heavy tanks. The Tiger II test had validated an approach. Quality steel, intelligent geometry, and high-velocity penetrators could match or exceed brute thickness. The 88 had not become weaker. The Allies had become measurably harder to kill. American metallurgy, casting techniques, and quality control had closed a gap that battlefield reports once suggested was unbridgeable. Engineers calculated that improving cast quality by 10% in hardness and reducing inclusions by 15% yielded a defensive improvement equivalent to adding 30mm of rolled plate, without the weight penalty. Geometry and chemistry were defeating mass. The myth of the 88mm gun as an invincible tank killer was unraveling in the cold precision of ballistic mathematics. The weapon remained dangerous, lethal, and effective against most Allied armor. But it was no longer absolute. The Jumbo proved that. The data proved that. The laboratory proved that. The war's narrative was shifting from German guns dominate to American engineering adapts, from myth to measurement, from fear to understanding. The Tiger II's failure at Isigny represented more than one test. It represented the collapse of an assumption that had shaped Allied tank doctrine since 1941. A railcar door slid open at a European siding. A T-26E-3 rolled onto the platform, its long 90mm barrel and sloped glacis marking it as something different from the thousands of Shermans that had preceded it. Days later, a Pershing engaged a Panther in the streets of Cologne. The footage would become iconic. United States armor had been accused of lagging German heavy designs since the Tiger I's debut in 1942. The T-26E-3 represented a rebalanced answer: 90mm M3 firepower, sloped armor, adequate mobility, and crucially, maintainability. The vehicle incorporated lessons from 3 years of armored warfare, including the findings at Isigny. Armor configuration. 102 mm at 46 degrees on the glacis. Turret front robust with cast geometry, approximately 114 mm effective. Weight in the 41 to 46 metric ton range depending on configuration, heavy by Sherman standards, but manageable by engineering and logistic systems designed for rapid deployment. The 90 mm gun M3 with HVAP M304 projectile delivered penetration performance approximately 178 mm at 1,000 meters range at specified obliquity. Against the Tiger II's frontal armor, the Pershing had a viable chance at ranges where the Sherman had none. Automotive. Ford GAF engine lineage, derived from proven V8 designs. Torquematic transmission. The drivetrain prioritized reliability over maximum power, a deliberate choice reflecting lessons from German over-engineering. Ordnance Committee authorization in early 1945 expedited shipment of pilot batches to Europe to meet enemy heavy armor on equal terms. The first 20 T-26E3s arrived in January. By March, additional units were in combat. Isigny's findings were a catalyst. The test proved that American metallurgy and geometry could resist German guns. The Pershing extended that logic to firepower. If armor could be made effective through intelligent design, so could guns. The 90 mm M3 firing improved ammunition represented that philosophy. On 6 March 1945, in the streets of Cologne, a Pershing crew spotted a Panther at approximately 800 meters. The engagement was brief. The 90 mm gun fired. The Panther burned. Combat camera footage captured the moment, and the images circulated rapidly through Allied commands. The Pershing was not a Tiger II equivalent. It was lighter, faster, easier to maintain, and easier to produce. It represented a different design philosophy. Balanced capability over single-dimension dominance. Within weeks of the Isigny trial, United States combat camera footage from Cologne showed a Pershing killing a Panther, the visual counterpart to the laboratory data. The Tiger II had forced the question, how do you fight heavy armor? The Pershing provided an answer, not by copying it, but by outthinking it. Combine adequate armor, superior mobility, effective firepower, and logistical sustainability. The sum of these advantages outweighed any single strength. The strategic lesson was profound. Winning required not the best tank, but the best system. A logistics clerk totaled copper, alloy steel, and man-hours per vehicle on a cost ledger. The numbers were stark, undeniable, and damning. The Tiger II's specification sought immunity. The ledger documented penalty. The same resources could field multiple Shermans, their crews, and a fully stocked supply chain. The arithmetic was brutal. Tiger II inputs. Approximately 300,000 man-hours per vehicle. Approximately 18 metric tons of alloy steel. Approximately 650 kilograms of copper. Specialized tooling, precision machining, and hand-fitted components throughout. Each vehicle represented an engineering triumph and an industrial catastrophe. Sherman M-Four-A-Three. Approximately 15,000 man-hours per vehicle. Approximately 9 metric tons of steel. Approximately 90 kilograms of copper. Modular construction. Interchangeable parts. Mass production techniques borrowed from automotive industry best practices. Battalion reports from Schwer Panzerabteilung 503 in March 1945 listed 32 tanks on roster, approximately 12 combat-ready on a given day. Fuel shortages, parts shortages, qualified crew shortages. The battalion existed on paper but barely functioned in reality. By contrast, United States armored divisions operated at 80 to 90% readiness. Replacement tanks arrived faster than losses accumulated. Spare parts flowed continuously. Fuel trucks never stopped rolling. A post-war interview attributed to Erwin Idders, one of the Tiger II's principal designers, recorded his reflection. We built fortresses that could not march. German staff papers from 1944 to 1945 echoed similar concerns. Overweight designs versus industrial capacity. Perfection versus production. Quality versus quantity. The Tiger II could, in theory, destroy any Allied tank it encountered. But encounters required movement. Movement required fuel. Fuel required logistics. Logistics required industrial capacity and secure supply lines. By April 1945, Germany possessed none of these in sufficient measure. Armor that could rarely reach decisive points, or that immobilized due to parts and fuel shortages, ceded initiative regardless of nominal gun or plate advantages. A Tiger II sitting immobile for lack of fuel was not a weapon, it was a target. A Tiger II abandoned for lack of spare parts was not a casualty. It was waste. The mathematics were unforgiving. Each Tiger II cost the equivalent of 20 Shermans in man-hours. Each Tiger II consumed the fuel of 3 Shermans for equivalent distance traveled. Each Tiger II required specialized transport, reinforced bridges, and heavy recovery assets that stretched logistics beyond breaking. In the month Pershings appeared in combat, German heavy battalions struggled to put even half their tanks onto the line. The Tiger II represented the logical extreme of a design philosophy that ignored everything except the single-tank engagement. It won duels. It lost campaigns. The paradox was complete. The vehicle designed to dominate had become a liability. Its strengths were negated by its weaknesses. Its capabilities were erased by its demands. The Tiger II proved that, in modern war, perfection could be the enemy of victory. The ledger did not lie. Production capacity, fuel supply, maintenance infrastructure, crew training, all of these determined combat power more than armor thickness or gun caliber. The Tiger II excelled in one dimension and failed in every other. The Shermans succeeded in aggregate. By April 1945, Allied intelligence estimated fewer than 40 operational Tiger IIs remained on the Western Front. Not because they had been destroyed in combat, most had not, but because they could not move, could not be repaired, could not be supplied. They sat in forests, in villages, along roadsides, magnificent and useless. The final accounting was mathematical. Germany invested 300,000 man-hours per tank and fielded dozens. America invested 15,000 man-hours per tank and fielded thousands. Germany's heavy battalions operated at 40% readiness. America's armored divisions operated at 90%. Germany's fuel production collapsed under bombing. America's fuel deliveries accelerated month by month. The Tiger II was not defeated by better armor or better guns. It was defeated by logistics, by production scale, by industrial democracy's capacity to deliver overwhelming material advantages sustained over time. The test at Isigny merely documented what the broader war had already decided. Quality without quantity is theory, not strategy. A bound report titled Examination of German Tiger B lay on a drafting table beside etched plate samples, ballistic test logs, and photographic plates. The document represented months of analysis, measurement, and calculation. Its conclusions would shape American armor doctrine for decades. Wartime lore had made the Tiger II a symbol of invincibility. Consolidated United States analysis marked it as a limit case of armor mass with declining returns under real industrial constraints. Summary tables equated jumbo cast-nose rolled homogeneous armor equivalent at approximately 190 to 210 millimeters depending on angle and curvature. Tiger II glassy, approximately 180 millimeters rolled homogeneous armor equivalency under specified test conversions and obliquities. Near parity, achieved through geometry and metallurgy rather than brute thickness. Recommendations emphasized slope, cast quality, shot design, and mobility over raw thickness. The report's technical sections outlined specific findings. Slope multipliers for cast armor, 1.3 to 1.5 depending on curvature. Optimal plate hardness, 240 to 260 Bernal. Projectile design improvements, ballistic cap optimization, core hardness matching, and sabot development. An Aberdeen summary line read, improvements in United States castings and projectiles offset enemy thickness. Further mass yields impractical penalties in mobility and upkeep. The report underpinned post-war United States tank design guidelines and NATO ballistic standards that privileged geometry and material science over thickness escalation. The M46, M47, M-Four-A-Three-E-Two all incorporated these lessons. Sloped glassy, high-velocity guns, balanced protection, reliable automotive systems. The Tiger II test proved that the giant, and the assault Sherman met near parity only because metallurgy and angle changed the equation. Thickness alone was not destiny. Engineering discipline, quality control, and intelligent design were. Engineers who worked the Isigny trials continued their careers shaping American armor development. The lessons became institutional knowledge. Cast armor techniques improved. Slope angles increased. Ammunition development accelerated. Every T-Series prototype and production tank bore the mark of those January days when the 88mm gun failed against American steel. The bound report circulated through ordnance schools, armor boards, and NATO technical committees. Its data appeared in classified briefings and open technical journals. The findings were unclassified by 1952, allowing broader dissemination. The invincible King Tiger had taught a final lesson: that invincibility itself was myth, and that victory belonged to those who measured, adapted, and outproduced their enemies. A doctrine board officer pointed to a chart, slope efficiency multipliers derived from European trials, including Isigny's approximately 1.4 figure for certain cast geometries. The chart had become foundational to post-war armor design philosophy. Pre-1944 thinking focused on thickness escalation. British and Soviet designs added plate upon plate. German designs pursued absolute frontal immunity. American designs, informed by Isigny and similar tests, encoded balance protection and efficient firepower. The United States M-46, M-47, and M-4A-Three-E-Two series continued the principles validated at Isigny. Sloped, glassy geometry. Robust cast turrets. High-velocity 90mm guns with improved ammunition. The lineage was direct and documented. Research and development emphasized HVAP and APCR evolution, capped shot improvements, and casting practices that delivered more protection per kilogram. Armor Research Foundation contracts investigated optimal slope angles, cast versus rolled trade-offs, and spaced armor concepts. A board note from 1951 read, ballistic efficiency improvements of approximately 35%, 1944 to 1949, achieved without gross mass increase. The Isigny test's influence extended beyond armor. It validated a systems approach to warfare. Logistics, production, crew training, maintenance infrastructure, fuel supply, all mattered as much as the tank itself. The Tiger II's failure proved that dominance in one dimension could not compensate for weakness in others. Allied success in 1945 rested not in miracle armor but in systems, production systems, logistics systems, engineering feedback loops that turned tests into field advantages. The Jumbo's resistance to the 88mm gun mattered because it could be produced, fielded, fueled, and repaired. The Tiger II's theoretical superiority mattered less because it could not. Fort Knox Armor School curricula incorporated the Isigny findings. Officer candidates studied the ballistic reports. Tank commanders learned that geometry multiplied effective thickness. Ordnance officers learned that quality control determined battlefield performance as much as design specifications. The lessons spread through NATO. British, French, Canadian, and other Allied nations reviewed the data. Cast armor techniques improved across Allied production. Ammunition standards harmonized around penetration requirements validated by tests like Isigny. The shared knowledge became a force multiplier. By the early 1950s, the Tiger II was remembered as a cautionary tale. A vehicle that sought perfection and achieved irrelevance. A weapon that dominated engagements but lost campaigns. An engineering marvel that illustrated the limits of engineering divorced from strategy. The King Tiger proved the diminishing returns of mass. The Isigny trials proved the compounding returns of engineering, disciplined, measured, and relentlessly practical. The 88mm gun's failure against the Jumbo became a pivot point, a moment when myth met measurement and measurement won. The war's final lesson was simple. Reality does not yield to reputation. Steel, chemistry, geometry, and logistics write history. Everything else is noise. The Tiger II from La Glise sits under museum lights now, restored and silent. Visitors walk around it, cameras raised, marveling at its size. 68 tons of metal, 180 millimeters of frontal armor. The long 8.8-centimeter gun angled slightly downward, frozen in permanent aim at nothing. Nearby, an M-Four-A-Three-E-Two Jumbo sits on display. Smaller, less imposing, but marked by the same history. The cast nose bears the scars of testing, gouges, craters, spall marks. The plate held. The crew would have survived. Between these two vehicles lies the story of January 1945. Not a story of heroes and villains, but of engineering, measurement, and the relentless discipline of evidence. The myth that one represented invincibility. The test that proved otherwise. The Isigny trials documented a truth that propaganda could not suppress. That armor, like all technology, obeys physics. That geometry and chemistry matter as much as thickness. That production capacity and logistics determine victory more than single-vehicle superiority. That systems defeat specifications. The 88mm gun's failure against the Jumbo was not an accident. It was the inevitable result of American metallurgy, casting technique, and quality control meeting German late-war material shortages and propellant degradation. It was measurement defeating myth. The Tiger II's operational failures were not bad luck. They were the predictable outcome of a design philosophy that ignored logistics, fuel consumption, maintenance requirements, and production scalability. It was reality-defeating theory. The war's outcome was not predetermined, but it was mathematical. Thousands of adequate tanks defeated dozens of perfect ones. Reliable supply lines defeated brilliant tactics. Democratic industrial capacity defeated authoritarian engineering obsession. The numbers never lied. Veterans of the armored divisions who fought against Tiger II's understood this. They respected the vehicle's firepower and armor. They also knew that for every Tiger II encountered, 10 never reached the battlefield. For every Tiger II destroyed in combat, 5 were abandoned for lack of fuel or parts. The algebra of war was unforgiving. The engineers who conducted the Isigny trials contributed something profound. They replaced fear with knowledge. Allied tank crews had fought for years believing German heavy armor was invincible. The tests proved it was not. That knowledge saved lives, not by changing the armor, but by changing understanding. Today, the reports from Isigny remain in military archives. Ballistic tables, metallurgical analyses, firing logs, photographs of struck plates, the paperwork of war as vital as any battlefield action. These documents shaped American armor development through the Cold War and beyond. Every M60, every M1 Abrams, every modern main battle tank carries lessons first documented on a French firing range in January 1945. The King Tiger and the Jumbo, sitting silent in museums, represent more than vehicles. They represent philosophies. One pursued perfection and achieved irrelevance. The other pursued adequacy and achieved victory. One trusted myth. The other trusted measurement. History rendered its verdict in steel, mathematics, and logistics. The rest is memory and respect for those who served. If you value documentary history built entirely on verified records and technical analysis, consider subscribing. Every episode is based on declassified archives, ordnance reports, and battlefield documentation, not fiction.